So here we go. Here's our data that we got, and you've plotted a graph and how wonderful things. And what we find is that, as we should sort of expect, as the temperature increases, well, then so does the pressure. That also increases. And if we think about what's going on inside that little bulb, we've got our particles, and that looks now like a weird disappointing cookie. Let's just take one in there. The temperature, it didn't need to increase its size. Temperature is a measure of how quickly it's moving around fast or slow, it's bouncing off the walls of our container. And the hotter it is, well, the faster it moves. Excellent. The hotter it is, the more collisions and the more force is, increases with each collision. So what we do find is that temperature and pressure are linked together. So one of the things that we learned just from looking at the results is that as temperature increases, the pressure increases. Because the first thing is collisions occur more often, and the second reach is that collisions exert a larger force. Okay, so the fact these two things happen make it probably fairly straightforward this does. So what did our graph look like? Well, our graph, depending on how you drew it and depending on your scale you took, looks a bit like this. So let's zoom in, because there's one thing we love to do, zoom in on a graph. Now, there's a bit of scatter because this is data taken in the lab. What we can do, take our ruler, and we stick this down and say, oh, look. Okay, I'm pretty happy with it. There being a straight line here. I don't need to go through that one, do I? So we can say, okay, what's the best sort of straightish sort of line I can do with this? Maybe something, maybe a bit like that, maybe. It's fairly good. Let's draw a straight line on it and see what we get. See if this looks okay. I found a use for the ruler tool. Right, go away, ruler. Yeah, I'm pretty happy with that. Okay, so we have a straight line. Hurrah. And the thing is physicists and generally people who do science, well, they like to think, well, what would happen if you went what happens if you go that way? Or what happens if you go this way? What occurs if you stretch off into one direction or another, where you've got a graph and you've got some kind of relationship? Because mathematically, I'm going to write some maths over here. Mathematically, if you saw a straight line on a graph, remembering this isn't going through 0, 0, you would write this as y is equal to mx plus c. That's how you would write this as a graph, like any straight line. And actually, we know is that our y is pressure and our x is temperature. So we might say that our pressure is equal to m, which is our gradient, times temperature plus some kind of the intercept, which is somewhere around there, so 90 something. And that might allow you to consider something. And the thing is unlike maths, where they're, in maths they're just kind of like, there's some variables, there's a y, there's an x, they're different. These things represent something, okay? And this y value represents pressure. And there is something to be considered about what happens if you keep going this way. If you keep going along this line, eventually you're going to cross a point where this pressure is equal to 0. Where the y value, a straight line, would eventually hit a point where pressure would be 0. And the question, therefore, is what does that mean? Well, let's go back to our little thing here and see what would that mean. Well, that would mean that these particles inside this container are no longer exerting any pressure on it. For P to be 0, there must be no pressure. But if there's no pressure, well, that must mean there must be collisions happening, not just less often, but never. There must never be collisions between these particles and the walls of this container. Now, you can't do that by imagining, the only way to do that is for these particles to no longer move. And this leads to this wonderful little concept called absolute zero. This straight line, this innocuous looking straight line, predicts that at some point the pressure is going to equal zero. And if the pressure equals zero, that could only be when our particles are no longer moving. And that is as stationary as anything can get. You can't move less than not moving at all. That puts some kind of limit to this thing, which says, there must be some temperature. There must be some temperature where the gas exerts no pressure because the particles have stopped. Well, they've got no kinetic energy. They are essentially stopped. And this, for this gas in this case that we've got here, well, we can try and work out what that temperature must be. Because what I've done is I've got the same graph now. Now, if you're mathematically inclined, you can do this by working out the gradient and plugging numbers in, and you get some answer. But sometimes it's nice to say, okay, well, here's the same line. Here's the data that we collected. I've shoved it all the way up here. So this is what we were able to measure. And we'd say, okay, well, where would this cross? And all we need to do is zoom back in because it's all very exciting. And let's cut our ruler back. Aha. So let's cut our ruler back. And let's see if we try and get a straight line. It's not right there. So what are we saying about those? Is that right? Maybe not quite yet. I feel quite good about that line actually. Maybe there. Yeah, that feels a bit better. Somewhere between there and there. I mean, now one of the things that's quite important to note is look how much when you're trying to make a prediction up here. Look how much this moves by. I mean, sort of from 34-degree angle slope to 28. So in the space of 6 degrees, that predicts a sort of range of 50-odd degrees. That feels about right to me. This one here. So let's go with this. Let's go with a green pen. See if we feel okay about it. Ooh, did not mean to do that. Yeah, that's okay. What we find is that, let's take our ruler away, we find that we're predicting somewhere in the region of minus 250 degrees Celsius that there is some form of temperature at which this gas would exert no pressure. Now, because there's scatter, there's uncertainty. I mean, if we were slightly going, oh, maybe it's sort of closer to this thing here, if we did the line like that, we'd end up with probably closer to about minus 270 if we went the other way. And this is the whole thing about uncertainty in measurements, how you can't, this is why it's important to collect data, especially if you're trying to predict something that's quite a long way out. These are all reasonable lines that end up somewhere when you're predicting all the way back. And in order to improve it, you'd want to collect data in this region that we don't know. We need to go below, we need to go well below. So maybe put it in some liquid nitrogen and so on. Anyway, so that gives us about maybe sort of like minus 270, and here would be about minus, let's say 220. So we've got this range here where we're predicting this sort of like unknowns in development. Now, what happened is this was kind of set upon, is that what physicists did is they did this kind of experiment. They went beyond the realms at which I'm able to go to. They were taking measurements down here, and they did it with multiple different types of gas over and over and over again. So, doing with different amounts of gas, different volumes, different things, and they found that no matter what gas you started with, you were ending up with a prediction that was somewhere around, this is not quite perfect, but somewhere around here. That all lines ultimately would intersect at a temperature of minus 273 degrees Celsius. The coldest that any gas could theoretically get to was this temperature. And this temperature became known as absolute zero because it was the predicted temperature at which the particles of any gas would stop moving. Okay, so we did it very quickly I did it very quickly in the lab with, just with normal air in a range of about 0 to 100 degrees. You keep doing it, you'll end up, you do it with any something. You can do it with pure oxygen or carbon dioxide or anything you want, or helium. Helium would be a great one. This is the temperature at which it predicted things would stop moving. So it allowed us to define something called absolute zero. So absolute zero was defined as the temperature at which particles would have zero kinetic energy, and it was measured, or it was sort of like measured to be at minus 273 degrees Celsius. And so that became this sort of number. Okay. Now, what this allowed physicists to do was to think, well, actually, the Celsius scale is something that we kind of base just on, the temperature of water. So our scale of temperature is that we have water, and when it's frozen, when it freezes, we say, well, that's 0, and then when it turns into sort of steam, I don't know why this for some reason, and we say that's 100 degrees C. And the generation of that was then we had these things that were called centigrade, but we didn't centimeter 100. We just then divided it, the difference between them, 100 or 100 lines. We just divided it into 100 equal units, and that gave us a Celsius scale. But of course, many things in the universe are colder than this. So we have negative temperatures. If you hang around with anyone in America who uses the Fahrenheit system, you end up with very, very bizarre sort of temperature scales that they use with Fahrenheit, where I think 0 degrees Celsius, 32 degrees Fahrenheit, I think. And I think body temperatures of 96 or 98 degrees Fahrenheit. Very, very sort of strange scale, that one is. But both the Fahrenheit scale and the Celsius scale are really based on things that we found and stuck thermometers into and said, right, here's how we're going to make it. Physicists now had some kind of temperature that actually represented 0. It is not possible to be colder than this temperature. You can't cool a gas down to minus 277 degrees Celsius or minus 300. This sort of region here was utterly forbidden. You can't be here. Here be monsters. Because you cannot have less than no kinetic energy. You're stationary. Doesn't make any sense to have, you can't move less than not moving at all. So what became introduced was a thing called, the Kelvin scale. The Kelvin scale of temperature starts at absolute. I can't spell the word 0. Starts at absolute 0. Absolute 0. Okay, so that's the Kelvin scale of temperature starts at absolute 0, but then happily tracks with in line with Kelvin. So a change, but once the physicists did a good idea, they did a good thing. A change of 1 Kelvin is equal to a change of 1 degrees C. So often when we're dealing with temperature changes, we don't need to faff around worrying about whether we're in Kelvin or Celsius. It's okay, but what it means is that essentially, if you want to convert from Kelvin to Celsius, you just need to convert by this 273. Okay, so so we can sort of say that, you know, 0 Kelvin is equal to minus 273 degrees Celsius. We can then say that, well, actually, what would happen if you added 273 to this to get to 0 Celsius, so the freezing point of water, you'd get that would be plus 273 Kelvin. Okay, I'm going to move this all down for a moment. I don't need this just yet. Go away. Okay, so if we want to go to 100 degrees C, so we want to go to boiling point, well, that's going to be 373 Kelvin. If you want to go to body temperature, so we want to go to 37 degrees C, well, what we do, 37 is 37 higher than this. We add 273 to our Celsius temperature to get the temperature in Kelvin. So we add a 7, so we get 280 plus 3, so 310 Kelvin. Okay, and this is how you convert between the two. It's a thing you need to do every now and again. So, so to convert from so to go to Kelvin to Celsius, we subtract 273 to convert from Celsius to Kelvin. We add 270. So that number 273, that's the important thing. Sometimes people are like, oh, which way do I do it? The key idea is that only Celsius can be negative. You cannot get negative numbers. So if you're going into Kelvin, the number has to get bigger. So to go into Kelvin, you're adding 273 because then you can never get. Now, what this means is we can redraw that graph. And this time, what I've done is I've added 273 to all the numbers. They're the same numbers as they were. It's the same graph. It's the same data. But I've done it in terms of, and this time, like this axis is temperature. That's not printed it out. This is temperature in Kelvin, and this is pressure in kilopascals. Well, let's see what this looks like. Let's get our ruler out, and starting at 0 this time, and we can think, well, what do we end up? Quite yet. Bit higher. There we go. Look at this. Oh, what a wonderful, joyous line. Happiness personified as the line on a graph. If we work in pressure as it normally is, but temperature in Kelvin, go away, I'm done with you now. Remember that when we were worrying about drawing things in Celsius, we had awfulness of like lines being over here, and we had to say, oh no, it's y equals mx plus c. But look what we get if we have it like this. We just have the wonderfulness of this thing is directly proportional to this thing, or pressure is directly proportional to temperature in Kelvin. And that is a wondrous thing, okay? Because if we think about what we met last time, with Boyle's law, when we had this, we could then say, oh, okay, remember that if you've got pressure is equal to some constant times the temperature in Kelvin, we should get pressure over temperature should always equal some constant. Should we? Well, let's have a little look at our data and see if that is indeed. Ooh. No, undo. Move my line. I want to move my line. Nope, my line is stuck to it. Let's undo that again. There we go. Right, okay. Last thing we do, let's just see if that is true. If we take the pressure and divide it by the temperature, do we get the same number each time? So let's try this. So 88.4 over 268, and we get 0.33. 94.2 over 283, we get 0.33. 99.2 over 293, and we get 0.34. Oh, slightly different. 102.3 divided by 308, and we get 0.33. Okay, and this is what will allow us next time to derive what we call the pressure law. But what we can see, much like Boyle's law, we've got a very similar pattern, which is that we have two of our key sort of like variables when we think about gases and gas pressure, which is the temperature the gas is at and the pressure it's exerting. And we're finding that there is a direct relationship between the two. But we have to, before we do that, we have to make sure that we're measuring this in Kelvin. Okay, that becomes essential. Just to prove that, if I take these numbers and say, well, can I, but you might notice this is going to go wrong very quickly if I try and do pressure over temperature up here, mostly because this first one's negative. So 88.4 over minus 5 is going to give me minus 17.7. Whereas 94.2 over 10 is going to give me plus 9.42, and then 99.2 over 20 is thinking about half that. So if we try and use 4.96, 96, no, this does not work. Sad. You know, trying to do this with Celsius and when we're Celsius, this doesn't work because the Celsius scale is only based on the fact we live on a planet with frozen and boiling water, whereas trying to do it with the Kelvin scale, this is good. This is what we'll use next time. Excellent. And there we go.